Hey guys, this is Mrs. Chabot. This is for Calculus 3. I had a question from section 14.4 on one of the problems that I believe doesn't have a view and example in my math lab work. So the directions say determine whether the curve uses arc length as a parameter. If not, find a description that uses arc length as the parameter. Okay, so this is the 10th question in 14.4. Those are the directions, and the given function is r of t equals the vector with components 4t squared, 8t squared, and square root of 89t squared, with t between 1 and 4. Your 10th question will look a little different, like the coefficients will be different, but the format should be pretty much the same. Okay, so this is paraphrasing theorem 14.3. So if we have some vector valued function r of t for t greater than or equal to some value a, arc length is given by s of t, which is the definite integral from a to t of the magnitude of v of u du. And of course, we're using v here as the derivative of r. And also in that theorem, if the magnitude of v equals 1 for all t greater than or equal to a, then t would correspond to the arc length. So the parameter t would be the same as the arc length there. So if the magnitude of v equals 1 for t between 1 and 4, then we would be done. But let's see what happens. All right, so let's take a look at r prime. Okay, so looking up at our function r, we get the derivative has components, 8t, 16t, and then 2 square root of 89t. All right, so let's find the magnitude of r prime or the magnitude of v, whichever notation you want to use. So you have the square root of 8t squared would be 64t squared, plus 16 squared is 256 times t squared, plus 2 squared 89t all squared would be 4 times 89t squared. And let's simplify that. So I'd add 64 plus 256 plus 4 times 89. Okay, and let's see what we got. Let's see. Okay, so we get the square root of 676 t squared. And remember, t was between 1 and 4, so t is positive. So this would just simplify to the square root of 676, which does simplify to 26 t. Okay, so we see that t is not the arc length here, but that is okay. We can find a different parameterization. We'll use S for arc length so that the parameterization will correspond exactly to the arc length. Okay. All right, so we want to use S, and so remember from that theorem, our arc length function, S of t, is it's still up here, so the definite integral from a to t. So in this case, remember t started at 1, so it'd go from 1 to t of the magnitude of v of u. So in this case, our magnitude of v is 26t, but if I'm using that dummy variable u, that would be 26u du. And let's just go ahead and evaluate that. All right, so the antiderivative of 26u is going to be 13u squared evaluated from 1 to t. So we'll get 13t squared minus 13 times 1 is 13. Okay, so our arc length, S of t, is 13t squared minus 13. So if I found the arc length when t equals 1, we could, take a look at what we have there. Okay, so in this case, like I said, so we would find the arc length for any value t between 1 and 4, but I want to be able to parameterize so that the arc length is the parameter. So let's solve for t here. So I have s equals 13t squared minus 13. Okay. So I have s plus 13 equals 13t squared. Okay, so I get t squared equals, I guess I'll write it as s plus 13 over 13. Okay, now I don't want to solve for t. I could, but I'm not going to here because then I'd be dealing with a square root. And in this case, I don't need to, because if you look back at our function, which is off the page now, but our original function was r of t, remember, was the function with components 4t squared, 8t squared, square root of 89t squared. So all of these have a t squared, so it'll make our lives a little bit easier just to substitute this whole expression in for t squared. So I'll have the vector with components. Oops. So what I want to do now is write this function with that new parameterization. So I'm going to use the parameter s, and I'll replace t squared with s plus 13 over 13, and so on for all of them. Okay, and so I don't know how you want to simplify this. It depends on your preference, but you could write this as s 13ths plus 1 and kind of distribute it that way, but I'll just factor out the 13 and write it that way. So I'll keep the s plus 13 in parentheses. Okay, all right, so I'll write it like this. All right, so my vector valued function r equals, I'll write 4/13 times s plus 13, so it looks a little bit nicer, 8/13 times s plus 13, and square root of 89 over 13 times s plus 13. Okay, so this vector valued function is going to draw the same curve as this vector valued function, but now we just changed the parameter, so be essentially tracing the curve at a different rate. All right, so two things. Remember back at the beginning, we had 1 was less than or equal to t is less than or equal to 4, so that's the part of the curve that we'd be tracing. So I need to make sure that I'm tracing the same exact thing when I change the parameter to this s. So when t equals 1, if we go back and look at our s here, remember it was 13 times t squared minus 13, so I'd be getting 0. Okay, and then, right, which makes sense like we talked about. If we plug in 1 for t, we'd get an arc length of 0. So now s is representing arc length. And then if t equals 4, we have s equals 13 times 4 squared minus 13. And so we'd find that and get 195. Okay, all right, so now we have our parameterization, and t was between 1 and 4. To get the same curve with our new parameter, we want to make sure that s is between 0 and 195. Okay, so we can see our arc length, if we go through the whole curve, is going from t equals 1 to 4, or from s goes from 0 to 195, is going to be a length of 195 units. So that gives us that. And if you want to check, if you look at the magnitude of r prime of s, you'll get 1, like we saw in the theorem. So if you take the derivative here, this would just be a constant. So this would be 4/13 squared plus, again, the derivative here would be 8/13. I'll square that. And then the derivative here would be square root of 89 over 13, square that. So we'd get, let's see, 16 plus 8 squared is 64 plus square root of 89 squared is 89 over 13 squared is 169. And then hopefully that, yes, it does add up to 169. So we get 1. So like we saw in the theorem, if this is the parameter, the magnitude of that v of t, or in this case v of s, will equal 1. Okay, well, I hope that helped. Sorry, this was a little long. And that's it. Have a good day.